Course-Elmogahzy Learning LLC introduces a new video course on cotton fiber to yarn technology and engineering. Dr. Elmogahzy is a professor of textile engineering with experience of over 40 years in the textile industry.
This video course expands over 40 sessions from fiber to yarn, and it covers both fundamental and practical aspects of the fiber to yarn system.
The challenges facing the fiber to yarn conversion system.
This chapter here will provide us with an overview of fiber to yarn engineering. And fiber to yarn engineering stems from many challenges that the spinner face every day. These challenges are being met using a wide range of practice. So we typically do not have a consistent way to meet the challenges facing the fiber to yarn conversion system. Many of these challenges are familiar, they are traditional, they are historical, and what I will do now is I will go over some of these challenges and discuss them a little bit before we go into the fiber to yarn engineering program, because based on these challenges we will see how a fiber to yarn engineering program is well justified. The number one challenge is the cost of raw material. Every spinner in the world understands that raw material represents a significant portion of the total yarn manufacturing cost. Every spinner knows that. But what we all need to understand is that the value of raw material is not fully reflected in the value of yarn. Meaning that despite the high contribution of the cost of raw material to the overall yarn manufacturing cost, an increase in the price of raw material today will not result in an increase in the price of yarn or retail product tomorrow. Why? Simply because the marketplace will not allow such a corresponding correlation. To explain this a little bit, a cost of raw material with respect to the overall cost of yarn manufacturing may actually range from about 50% to 70%. The cost of yarn with respect to the overall manufacturing cost of a retail textile product may range from 30 to 60%. This is a very significant cost, and you may want to do your own calculations to find out exactly what is or where you fit in this range here. That is, how much the cost of your raw material contribute to the overall yarn manufacturing cost. Following this scheme here, if we look at the value now, what we will find that the correlation between the value of fibers or cotton and the value of yarn is almost insignificant. And the correlation between the value of yarn and the retail product is also insignificant. One exception to that is the very, very fine yarn, which has a very specific market niche. So we know that we're making this fine yarn to be used in high quality product. And even with that, the exception is not so much of an exception, because the correlation there would be about 0.6 to 0.7 correlation. What does this correlation means? Well, to illustrate the meaning of this correlation, let us go back to 1994, when the cotton price was doubled from what, 55, 60 cents a pound all the way up to almost $1.05, $1.10 per pound. That was a substantial increase that took place in a very short period of time. During the same time, what happened to the yarn price? Almost nothing. It stays the same, and in many cases it was declining. So that is the dilemma that we face here. This is the challenge that we face here, is that the spinner today, the margin of profit to the spinner today is highly vulnerable to the swinging price in the raw material. The raw material price can double tomorrow, but that will not be reflected in the yarn value in the marketplace. So this is something that we ought to think about it a little bit and see how can we narrow the gap between the cost-to-cost correlation and the value-to-value correlation.
The year 2011 to 2012 was truly an exception. In this period, yarn price increased as a result of an increase in cotton price to more than $2 per pound. This was the second highest increase in cotton price in history. But the increase in yarn price during this period was not only a result of an increase in the price of raw material. It was also a result of an overall shortage in yarn and fabric supply worldwide.
This is a simple pie chart that we did in a textile mill producing a rotor yarn of English count 20. And as you can see here, the cotton cost contribution was as high as 74% to the overall cost of the yarn manufacturing. The other 20%, 26% was distributed over other sources of cost, such as depreciation, supplies, packing, power, miscellaneous, labor, fringes, and so on. I urge you to repeat this pie chart in your facilities to see exactly what is the cost contribution of raw material to your overall yarn manufacturing cost. We have a major contribution of the cost of raw material to our end product, yet the value of the raw material is not fully reflected in the value of the yarn. How can we close this gap is very, very important. And perhaps the first step to close this gap is to start looking at the sources of cost, because cost of raw material is not just the price of raw material, but there are other factors that add to the cost. Sources of cost. What makes the cost of raw material that high? Well, the one obvious reason is the price of raw material. We are all happy when cotton is cheap. Not only that, the cotton department or the people that buy the cotton try their very best to look for discount cotton. And that's why sometimes we have a problem, because you buy a discount cotton and then you find out that it was not all that discount, because what you saved in the raw material is quite often reflected in a cost added in manufacturing and processing. So we need to be very careful in that. But price is the number one factor contributing to the cost of raw material. But there are other sources. Look at the waste. This is a major opportunity for all of us to reduce the cost of raw material. The fact is, waste is larger than ever. The reason for that is the high-speed technology we have today. At high speed, the segregation between trash particles and fibers, sometimes good fibers, is not as good as it is at low speed. So as a result of that, our waste today has a great deal of fibers, and I'm talking good fibers. The other source, which not many of us or think about that much, is the fiber to yarn conversion efficiency. You know, we need to ask ourselves whether we really utilizing the raw material into a yarn to its ultimate potential. And you know, to give you an example that many spinners is familiar with, is that look at the strength ratio. Look at the yarn strength versus fiber strength. We call it strength efficiency. You will find that the yarn strength to fiber strength efficiency range typically between 55% to 95%. In other words, some companies are able to convert the strength of the fibers almost perfectly to the strength of the yarn. Others are not. So here is the key issue here. Are we really converting the fiber attributes to a yarn attribute, in the sense that we can utilize all these attributes in the yarn characteristics? What is our efficiency of conversion? This is a key issue, and we must look at this seriously, because if we're going to pay premium price to the fibers, then we might as well finish the job by trying to use the fibers or utilize the fibers to their ultimate potentials in the yarn. In other words, do not buy a high quality fibers and produce a low quality yarn. And believe me, this happens quite often in our industry. So sources of cost of raw material involve price, waste, and the fiber to yarn conversion system. You need to look at this very carefully, because for a company producing a certain product, when they go out and shop for raw material, they have a very narrow range of raw material. They know exactly what raw material they need. So if you compare in between two companies, both are producing denim, for example, or towels or sheets or whatever, we will find that these two companies, when they go out, they actually look for fiber attributes that are within very similar ranges. So what distinguishes between this company and that company would be actually the other aspects, the waste and the fiber to yarn conversion efficiency. This is what makes one company more superior or better than another, especially when it comes to the profit making. As I mentioned earlier, waste distribution or cost distribution, I mean, is not just waste, but also fiber to yarn conversion efficiency. That is, are we using the raw material we have to its ultimate potential in the yarn? How much is your yarn to fiber strength efficiency? How much is your yarn to sliver, for example, nips efficiency or deficiency in this case? There are many factors here that if we look at them closely, we can save a great deal of effort and money, and we can certainly reduce the cost of raw material. The key here is understanding the technological limitation. How far can we push the machine to produce something? And the second factor is to understand the fiber-machine interaction. The profit margin is largely a function of the extent of raw material utilization. The price of raw material for a given product falls within a narrow range. So the key issue here is, given a certain price of raw material, okay, which is just one factor, it's a major factor, but it's only one factor of our overall cost of raw material, can we seek other factors that are cost added and reduce these factors so that we can benefit the most from the raw material that we buy, so that we can convert the value of raw material to a value of yarn. The profit margin is largely a function of the extent of raw material utilization and the quality of yarn. The extent of raw material utilization varies widely depending on many factors. The extent of knowledge of spinning technology, fiber quality, and the yarn quality. The spinner today must understand the role of fibers in making a good yarn, because the role of fiber is critical, and it's becoming more and more critical as we face new technologies at high speed that demand higher fiber quality. It's very important that the spinner communicates with the cotton department, with the people that buy cotton, on what fiber attributes will provide an optimum yarn and an optimum processing performance. Very, very important. I cannot imagine a spinner today that has no knowledge of the fiber attributes and of the role of fibers in making a good yarn. Now, these three issues here are discussed in great detail in this course. We will talk about spinning technology, we will talk about fiber quality, and we will talk about yarn quality. These are separate chapters, and some of these chapters will actually take many hours to fully cover all the materials in these chapters. The second factor to maximize the utilization of raw material is to understand the concept of cotton mixing. Cotton mixing is not just a use of a good advanced software and a computer to select cotton beds from the warehouse. Cotton mixing is a science, and you will see in one of the chapters of this course how scientific the cotton mixing procedure is, and how understanding the scientific aspects and the underlying concept of fiber mixing will help you improve in the yarn quality. Cotton mixing. We need to understand the fiber selection as well as fiber blending. These are major issues that the spinner must understand. The spinner must also understand the extent of translating the selected fiber attributes into the desirable yarn characteristics. That is the fiber-to-yarn modeling. This is a very serious issue here, because as I go around and deal with different textile mills, I find that very few of these mills utilize some form of modeling. A fiber-to-yarn modeling means fiber-to-yarn relationship, meaning that you have a tool by which you can predict the quality of yarn prior to processing the fibers. And the impact of that, not only careful selection of the fibers, but also careful purchasing of the fibers. Remember, we're talking about cost here. So understanding what fiber constitute the best yarn quality of your yarn requires modeling of some form. You cannot just sit around the table and say, well, we need fibers of short fiber content and higher strength and fine count or fine micronair or a little bit longer length, so we can produce a yarn that will give us a strength of 15 or 16 gram per tex. This subjective way of putting things together simply does not help very much, and when problems happen, we wonder why. And I'm not saying that these approaches are bad. Of course, many people work in the spinning line, and many people work in the fiber to yarn conversion system have a great deal of experience, and they can easily determine what good fibers or what fibers are good for their yarn. But good and bad is not enough. We need to be extremely accurate on what levels of fiber attributes that are required for our yarn. Because believe me, most of us know that just 1 point difference can result in a major saving in the price of raw material, even by the market standards. So being specific is extremely important. And the only way to achieve that is through a fiber-to-yarn modeling or fiber-to-yarn relationships. These relationships will help us understand the impact, the magnitude of the impact of fiber properties on yarn properties. It will help us predict the yarn quality prior to processing fibers. That is the key. The spinner should also understand the system theory, how the technology works. And that is through understanding of the fiber-machine interaction. Well, as I go around, I find that most spinners have a great deal of experience and knowledge of the fiber-machine interaction. I have no doubt about that. But I also find that if I compare 8 or 12 carding machines that are taken from the same opening in the cleaning line, that the variation between these cards are tremendous. So what we are talking about here is inconsistency of the performance of different machines. This issue here lies in the heart of understanding fiber-machine interaction. Why one unit performs better or different than another unit? Because our problem is consistency. So part of understanding the system theory is to look at different units in your processing line and see how they interact with fibers, how they alter the fiber properties, and how certain attributes or certain levels of fiber attributes can actually affect the performance of some of your machines. This is a major issue. What happened to fiber length as we go down the chain of processing? What happened to fiber fineness as we go down the chain of processing? What happened to strength of the fibers? What happened to the color? what happened to the trash, what happened to the short fiber content, and so on. This is a major issue, and we will discuss that in a separate chapter that is titled Fiber-Machine Interaction. Another factor is the extent of translating the value of fiber into an acceptable yarn value. And if we have a good understanding of the cotton mixing process, that's the fiber selection and blending, and the good understanding of the fiber machine interaction, and if we in fact have models that relate fibers to yarns, combine all of these together, and that will provide you with tools that are extremely useful in improving the extent of translating the value of fibers into an acceptable yarn value. But in this course, in addition to all of that, we discuss a mechanism, a model that will help you actually achieving that. We call that the technological value model, which deals specifically with determining the technological value of fibers. The fact is, in most cases, there is quite a gap between the market value of fibers and the technological worth of the fibers. We don't have perfect communication between the spinner and the cotton producer or the fiber producer. And as a result of the imperfection of this communication, and as a result of the mixed signals that the fiber producers receive from the yarn spinners, we see that there is quite a gap between the market value of fibers and the technological worth of fibers. The second challenge that we face is the pressure imposed by new technology. This is a very, very critical challenge. Well, many of us know that new technologies impose more constraints on the quality of raw material. The new technologies are demanding the continuous increase of speed and production rates have not come at no price. The price is more constraints on the fiber quality and the more demanding approach to what fiber attributes should be used in the new technology. Today's machinery is substantially expensive. We all know that. But to make matters additionally complex, machines become obsolete before they depreciate. So now we have a revolutionary technology, but it doesn't last that long. And there is a gap that has been created between the learning curve of the technology and the lasting period of the technology. So every time we think that we understood the technology fully, a new technology come around, and then we have to start the curve all over again. What does that mean? It really means that we are under tremendous pressure to learn a great deal about the new technology in a very short period of time. Every time I turn around, there is a new spinning system out, there is a new weaving technologies out, and we need to learn about all of that, especially if we're going to make decisions about buying this expensive technology. Labor cost is in a continuous rise. But the reality is automation plus information, which are basically the two main features of the new technology, should lead to redistribution of personnel assignments and duties. This is an issue that I find it to be missing in many of the textile companies that I work with. Is we have state-of-the-art technology, so all the automation, all the control, and all the information systems, yet we're dealing with this state-of-the-art technology using old approaches, using the traditional way of handling the operations. We need to understand that in the very near future, your personnel will not be managing other personnel and will not be operating machines. Your personnel will be managing data and information. This is the key to any successful utilization of the new technology. Our industry is still a labor-intense industry. And the question is not so much of getting rid of people as much as reutilizing or reassigning or distributing the job functions in view of the technology that we're dealing with today. This technology is very, very expensive, and I cannot think of any way to justify this high technology except better utilization of personnel functions and personnel assignments. The third challenge is the cost of quality, and this is a traditional challenge in our industry. For some reasons, and don't get me wrong, not all our industries like that. There are many textile companies that are doing just great. Of course, I cannot mention names here, but the truth is there are many very good industries, many good companies in our industry. But a great percentage of our companies are still lagging behind when it comes to understanding the cost of quality. Today's quality problems are substantially expensive. If one would take a look at a book written about quality in textiles that was published, say, 50 years ago. In fact, I have a couple in my office. One published in 1930, the other one published in 1945. And look at these books and look at the list of quality problems facing the textile industry, then you will be amazed to know that those problems are the same problems we're facing today. Yarn imperfections, weak yarns, fabric defects, spinning ends down, warp stops, filling stops, carding stops. All of these problems are historical. They are traditional. I mean, come on, you would think that some of these problems should have been eliminated by now. Well, I hate to add this to this fact, and that is the yarn today. The quality of the yarn today is largely inferior to the quality of the yarn in the early 80s. And this is also evident if you look at yarn imperfections. Tremendously higher today than they were years ago. So the approach that we're taking is not working, which is really the problem-solving approach. We lack some development touch to our daily activities. Today's quality problems are substantially expensive. Prevention in the first place is the way of the future. The next challenge is variability and subjectivity. Variability. Variability, as we all know, is an inevitable factor in the textile process. We have a great deal of variability. Process added variability, raw material variability, end product variability. Many undesirable features of the textile product are due to variability. And certainly some desirable features are also due to variability. So it's one of those things that we simply cannot live with and we cannot live without. But most of the time we cannot live with. The way we handle variability in a typical textile process is through two main phases of activities. Number one, analysis of variability, and number two, manipulation of variability. We do analyze variability on a daily basis. We do measure variability. There is no industry in the world that uses the so-called CV more than the textile industry. CV thickness, CV count, CV strength. I mean, just CV is almost a household term in our industry. So we analyze it. A great deal of analysis. And we also manipulate variability. And variability manipulation is something that is unique to our industry. In fact, many industries are not even aware of this concept. Many statisticians are not even aware of how to manipulate variability, despite the fact that they may have a PhD in the variability theory. Our industry has invented the variability manipulation concept. And by that I mean taken a very highly variable raw material and convert it into what? One of the misconceptions is that we convert it into a uniform yarn or a uniform fabric. Well, let me correct you. We don't convert a highly variable raw material to a uniform yarn or a uniform fabric. But what we actually do is we convert the highly variable raw material into a consistently variable yarn. Our yarn is variable, highly variable. And all what it takes you is just to take a look at the yarn under a microscope and you're going to see all types of variability. Thick, thin places, hairiness, nips, everything. But the fact that this level of variability is maintained consistent from one package to another, from one shipment to another, is the key. So the way we handle variability is through manipulation. We try to keep our variability consistent day in and day out. So that is how we manipulate variability, and we will discuss that a great deal. But the key issue in dealing and manipulating variability is fiber selection and the blending. Any spinner today ought to understand the underlying concepts of fiber selection and the blending, because this is the key to an excellent manipulation of variability. This is the key to avoid chaotic changes that often happen. The yarn is okay today and then tomorrow there is a problem. Manipulation of variability. We have to have a system that is robust against chaotic changes. We will discuss that a great deal when we talk about fiber selection and the blending. The traditional subjectivity of evaluating textile quality must give way to more objective approaches. Now, every time I talk about subjectivity, I get people that are really very defensive about that. They say, well, this is the oldest industry in the world, and we rely so much on art and experience and all of that. Well, I don't have any problem with that. Art and experience should always be a part of our industry. But that doesn't mean that art and experience should be implemented at the expense of scientific, proven, or practically proven techniques. The traditional subjectivity must give way to more objective procedures. You can take a look at the user statistics to find the evidence of why subjectivity, although we have implemented subjectivity over the years, is not working for us. Take a look at this. This is a simple table that summarizes for you the 5% user statistics and the 95% user statistics. This table is showing us here is that for carded ring span 100% cotton of count range from 7 to 15 English count, that there is quite a gap between the 5% top companies in the world and the rest of the world. In yarn strength, we have 50% difference. So for a given count, some company may be making 16 centinewton per tex, and another company is making 23. If you go to the variation in yarn count, which has improved a great deal over the years, we still find some companies that are producing yarn of that same range from 5.5 to 3.5 CV English count. Far off the top 5% that are making yarn from 0.7 to 1 CV. That's about 80% difference. If you look at yarn imperfections, which I mentioned a minute ago, the difference can be as high as 95% between the top 5% statistics and the rest. This is a serious comparison. And of course, you can argue that these differences may be due to differences in raw material, may be due to differences in technology. Well, we have examined all of that. We have examined the contribution of raw material to this substantial difference, as well as the contribution of the technology to this substantial difference. And what we simply found out is that, yes, raw material will have a great deal of impact on this difference. And if that means anything, it simply means subjectivity of fiber selection. The spinner still struggling with what fiber attributes or what fiber properties are suitable for his or her yarn. Now, between the raw material and the technology, the system theory or the fiber machine interaction that we discussed earlier. And that is where we found the major gap, because we looked at some companies that are using almost the same raw material, identical technology, yet the yarn quality here is quite superior to the yarn quality there. So these stunning differences in the user statistics imply or reflect a great deal of subjectivity of purchasing raw material, selecting fiber attributes that are suitable for a given yarn, and also reflect a great deal of subjectivity on handling the technology or understanding the fiber-machine interaction. These 2 points are focus points. They are points of emphasis in this course. And I'm hoping that by the end of this course, you will learn much more about these 2 issues and how they affect the quality of your product. The question now before us is, how can we meet these challenges? Well, there is a number of components that must be put together to provide an objective approach to meet these challenges. First of all, we need to evaluate our current practice. We need to evaluate the current approach. Typically speaking, any industry should have 4 main types of activities: product development, design, manufacturing, and problem solving. These are the basic activities in any industry. If we look at the percentage involvement of personnel in these activities, the trend or the common approach follows this curve here. Meaning that our daily activities are primarily manufacturing and problem solving. Particularly problem solving. Of course, manufacturing is #1 job. But we do much more of problem solving than we do product development and design. Well, as I mentioned a minute ago, we need to admit that the problem solving approach is not working. If the problems that we listed 50, 60 years ago still exist today, and at higher cost because of the higher production rate, then we know now that the problem-solving approach is not the solution and is not the way of the future. A more effective approach should follow the opposite trend. We should be doing much more of product development and design, because if our involvement is heavily focused on these 2 activities, I promise you, problem solving will be a minimum activity in our daily practice. This is the key. And obviously, if your company is doing much more problem solving now and much less of product development and design, there will be a transitional period in which you can convert your company into a product development and design oriented company rather than a problem solving industry. The problem solving is a very, very costly approach, and I could speak for 2 hours about that. 99% of the phone calls that I get from different companies are about problems, about disputes between the yarn or the fabric producer and the customer. This is the activity cycle, problem solving every day. So why is the problem solving approach is the common one? Because of the old traditional common philosophy that we have to maintain a balance between what we think is an appropriate percent defects and the cost expected to reduce this percent further. This is the common approach. Common philosophy is that if we have a percentage of defect, say 5%, and of course defects here could mean anything else. It could mean ends down, it could mean warp stops, it could mean fabric defects or yarn imperfections. Then quite often the way we think of these defects is primarily based on how much it will cost us to reduce these defects. We know it costs us. This is the cost of these percent defects. But because we realize that if we try to reduce these defects, it will cost us more money, then we simply learn how to live with the problem. This is the common philosophy. The common philosophy is we think that every problem we have, in order to be solved, it will cost us money. The cost-effective philosophy is based on challenging our intelligence to break the balance. This is a very important issue. If you go and look at the cost of improving quality, you will find that the cost of improving quality lies in our intelligence. You know, Grosby said that the cost of zero defects is zero money. Well, I'm not going to go that far. I'm going to say that intelligence is a key. Are we really challenging our people enough to remove the defects and the quality problems that we face every day? So going back to our balance, in my opinion, that in order to reduce these defects, all what we need is intelligence, much more than any cost. So we need to seek alternatives. And the key to alternatives is the fiber-to-yarn engineering. The focus of this course, fiber-to-yarn engineering. Fiber-to-yarn engineering is generally defined as a practically proven scientific approach in which the fiber-to-yarn conversion system is optimized with respect to two basic elements. Number one, the fiber-to-yarn quality-cost ratio. If we can optimize this ratio, then we will improve the value-to-value correlation that we mentioned early on. Number two, the yarn-to-fabric quality-cost ratio, because yarn is about fabric. Yarn by itself is not typically an end product. It will have to be used in making a fabric, a net or woven and so on. So any effort that we do to improve the quality-cost ratio in the yarn manufacturing sector will certainly result in reducing or optimizing the quality-cost ratio in the yarn-to-fabric sector.
Did you know that using a combed fine yarn will increase the cost of weaving manufacturing, but it may possibly decrease the cost of knitting manufacturing? Simply, do the math based on the fabric yardage produced in each case to find out.
Fiber-to-yarn engineering stems from quality engineering. In a quality engineering system, the goal is to design out loss and design in quality. And that happens simultaneously. As you design out loss, you will be designing in quality. As you seek ways to make your product consistently variable, not chaotically variable, then you're designing in quality. And as you design out loss, design in quality, the margin of profit will certainly improve a great deal. Fiber-to-yarn engineering consists of four primary phases. The first phase is fiber selection and blending. The second phase is the analysis of fiber-machine interaction, understanding the system theory, as I mentioned earlier on. The third phase is modeling the fiber-to-yarn system. And the final phase is determining the technological value of fiber. Now, these four phases initially should be followed in the order that I mentioned. We have to look at the fiber selection and blending, First, we have to then look at the analysis of fiber-machine interaction, because we know now that we selected the fibers properly. And then once we established understanding of the concept of fiber selection and the blending, and we know we're doing a good job in that, and once we establish a good understanding of the fiber-machine interaction or the system theory, we can then develop models that will relate the yarn properties to the fiber properties. And after we do all of this, we can utilize all of these phases to develop the ultimate tool, which is determining the technological value of fiber. This is the major cost, remember? This is where our emphasis, our effort. The top 5% of the companies in the world build their success on the fiber selection. On what value of fibers they ought to use or ought to pay. So this is the ultimate goal. So in the initial process we have to go in this order, but ultimately as we entertain each phase, the 4 phases will interact with one another. We'll have to integrate all these phases together to perform an optimum quality-cost ratio.